category systems and holography. Please take it away.
Thank you very much for introduction, Ibrahim. And first of all, I'd like to thank the organizer for giving me a chance to speak here. So today, I'd like to introduce one generalization of the entanglement entropy, which we will call pseudoentropy. And this generalization is based on originally some holography argument, which I will tell you soon. This is basically the generalization of the usual density matrix to the so-called transition matrix, where we have two different states, the bra and ket. And of course, such a transition matrix is no longer physical state since it's no longer Hermitian, for example. Nevertheless, as we will see later, pseudoentropy, entanglement entropy associated with such a transition matrix has a very nice interpretation as the number of E-pair pairs. And also, I will tell you its gravity dual in the context of radiation-shifted correspondence. And finally, I will also mention some possible interesting application of such a pseudoentropy in the context of condensed matter physics by using a simple transverse Ising model where we can answer the question whether a given two state belongs to the same quantum phase or not by a pseudoentropy. So this talk is mostly based on already published two papers, this one with Yoshigumi Nakata, Tadashi Takayanagi, Yusuke Taki, Jisha Wei, Ari Morabashi, and Nobuo Shiba. And we also mentioned a little bit about some work in progress. So although there has been already many interesting talk about important relation between entropy and area in the quantum gravity, but let me also briefly review it since it's also relevant to my talk. So there has been very profound connection between entropy and the area in the quantum gravity. One of the most famous example is the Bekenstein-Hawking entropy, where we have the relation between thermodynamical entropy of the black hole and its area of the horizon. And it's very surprising because it doesn't follow some standard volume law, rather it's a kind of area law. But once you notice this is a kind of area law in the lower dimension, it can actually tell us some very important feature of the quantum gravity. And it is actually the first starting point of the idea of the holographic principle, where quantum gravity may be described as the lower dimensional quantum many-body systems. And there is a radiation-shifted correspondence, which is a concrete realization of such a holographic principle in the string theory. We have a more fine-grained version of the relation between entanglement entropy. This is just a fine-grained entropy and the area of so-called minimal surfaces. So this is just a relation between quantum information theoretic quantity and area of the quantum gravity in ADCFT. So of course, we have already discussed very important quantum corrections or non-perturbative correction of this formula, but since we totally today focus on the classical part, so let me not writing this remaining pieces here. And additional comment for the later convenience is that this relation between entropy, entanglement entropy, quantum information theoretic quantity, and area is the relation between area of the Lorentzian spacetime, Lorentzian signature spacetime in the gravity side. Okay, so then from the gravity perspective, we have a very naive question. We know that at least ADS-shifted correspondence can work even in the Euclidean signature spacetime. Maybe I have to say space. For example, here I'm writing the very familiar example in the context of ADS-shifted. We have two different states where we act some local operator on the vacuum state, but this psi and phi state are the different. Then we can consider some inner product of G state. And we have some connection to the gravity side via standard GKP-Witten relation in ADS-CFT. So we have some dual semi-classical geometry related to this inner product. In the gravity side, at least, we can again define the minimal surfaces, which is the codimension surfaces anchored on the subsystem of our boundary. And if this psi and phi state are the same, we have some reflection symmetry. And in this case, actually, we can analytically continue this setup to the Lorentzian signature. In this case, these minimal surfaces can be related to the previous minimal surfaces in the Lorentzian spacetime. It means that it's related to the entanglement entropy. However, this is not the case for more generic two different states like this. Then it's not natural to ask what is the boundary counterpart of such a generalization of the minimal surfaces in the Euclidean signature. And this is our starting point of discussion. And today I will give you one answer of this question. Yes, it is indeed so-called pseudoentropy. So from now, let me introduce what is a pseudoentropy. So I will today tell you three things. First of all, I will introduce some basic ingredient to define the pseudoentropy, and then give you some nice interpretation based on the number of EPR pairs. And then I will have some comment about gravity there, although we have already discussed a little bit. And finally, I discuss some transverse Ising model as an example of the simple condensed matter physics. Then we discuss, as we will see, pseudoentropy can be a diagonals of the question whether two different states belong to the same quantum phase or not. Okay, so let me start for the detail. So since we are not thinking about usual density matrix, please let me mention again. So usually we think about density matrix. So, and by the way, today I just focus on the pure state and it's reduced density matrix. And we postpone for the mixed state generalization. In the pure state, density matrix should take this form, and it can be related to the expectation value by a trace of this form. On the other hand, we can, of course, naively generalize it to the two different states. And here, I assume this phi and psi state are not also orthogonal to each other in the rest of my talk. And this, let's say, transition matrix is no longer physical state. It's obviously not Hermitian matrix, but it can be appear in the context of so-called post-selection process. So we can also post-select the final state of our measurement. And in such process, we can define so-called weak value. And this weak value takes this form, and it can be related to some similar form of the expectation value. Here, I just replace usual physical density matrix to the transition matrix. And as expected, this weak value should take complex value in general. But anyway, in this way, transition matrix can naturally appear in such a more general procedure like post-selection. Okay, based on this, let's define the pseudoentropy. So this is simply the generalization of the usual entanglement entropy just by replacing the reduced density matrix to the now reduced transition matrix. So just we trace over subsystem a complement of the original transition matrix, and then we can define, let's say, reduced transition matrix. And then we can, roughly speaking, define pseudoentropy as the von Neumann entropy associated with this reduced density transition matrix. To be precise, we have to care about this definition, since generically speaking, transition matrix or its reduced version cannot diagonalize in the usual sense. But we can make our argument more precise by using some Renyi version. But since it's a bit technical detail, so let me skip here, but let me stress that we have a precise definition. Okay, here are some comments. And first of all, as expected, pseudoentropy for the generic two different states can take some complex value. It sounds a bit unusual, but actually in some nice class of states, pseudoentropy turns out to be real non-negative. For example, as we will see later, we can prepare ground states of the transverse Ising model. So here I'm just writing the Hamiltonian of the transverse Ising model with different coupling 1 and 2 for each J and H. Then, of course, we have some two different ground states depending on the coupling, and we can cook up the transition matrix between these two different vacuum states, ground states. Then it turns out that the pseudoentropy associated with this transition matrix gives us a real non-negative value. And another nice example is holographic state. I mean, the CFT state dual to the semi-classical geometry in the ADS-CFT correspondence. And since, as I have already told you, such a case, pseudoentropy is related to the area of the certain surfaces. So it's basically non-negative and also real, as long as we think about the non-complex metric. So in this talk, let me focus on the real part of the pseudoentropy, since today we just focus on such a nice class of states. And in this case, actually, there is a nice interpretation based on the number of distillable EPR pairs. So let me explain this from next slide. So, but before going to the pseudoentropy, it's great to start from the entanglement entropy, since it's more familiar. Entanglement entropy can be also regarded as the number of distillable EPR pairs under the so-called LOCC process. So here I'm just writing the one specific state psi of our interest. And in principle, it should have very complicated quantum correlation between subsystem A and its complement. But we can do so-called LOCC process in such a way that eventually we obtain, or we can somehow rearrange the pattern of the quantum correlation in such a way that we have a bunch of EPR pairs between A and its complement. So here we use the so-called LOCC process, which consists from the local operation acting only on the subsystem A or its complement. And we can allow some non-local communication between its A and its complement. But here, we just allow us to use classical communications, like email or phone call and something like that. Okay, and under this condition, we can first start from the small n copy of the original initial state. And then let's suppose we obtain capital N copy of the EPR pairs as the final result. Then we can compute the ratio between these two numbers and take small n to the infinity limit. Under this asymptotic limit, we can show that the value of entanglement entropy associated with this state, and then we can obtain reduced density matrix. From this, we can show that entanglement entropy is actually equivalent to this number of distillable EPR pairs under the asymptotic limit. Okay, and this is very well-known fact in the quantum information theoretic community. And then we can slightly generalize this procedure to the post-selected process. So we can do another things. After this LOCC process, we can do some post-selection. And then let's suppose we have some steps bar phi as the final state under the post-selection process. Then again, we can estimate this capital N in this setup. And again, we can compute a similar ratio between capital N and small n. And it turns out that this ratio now equivalent to the value of the pseudoentropy that we have already defined in the previous slide. But let me stress that this explanation, we can only do this for the very specific class of the transition matrix, where reduced transition matrix is Hermitian and real positive. If not, in general, we have, for example, complex value pseudoentropy. And in this case, we cannot use this argument for now. So this is just an interpretation, but it's really nice interpretation so far. Okay, so I have explained the interpretation of pseudoentropy as the number of distillable EPR pairs and the standard LOCC process plus post-selection. This post-selection is a new things compared with the entanglement entropy. Okay, then let's move to the gravity side. So though I have already explained the holographic counterpart of the pseudoentropy, which was rather original motivation of this talk, but let me explain it again. So let's suppose our initial and final state in the transition matrix has some simple gravity dual in the context of ADS-CFT. Then we can consider inner product of these two states, and it's holographically dual to the certain Euclidean signature asymptotically ADS space. It can be understood from the standard GKP-Witten relation. And then it turns out that the area of the minimal surfaces on this Euclidean signature background, and it's important to note that this Euclidean time direction has some non-trivial evolution. So this is just a Euclidean time-dependent background. So this area divided by 4G Newton turns out to be equivalent to the pseudoentropy of our interest. And to prove this, it's actually very straightforward. We just reused the standard Lukowitz-Marduk-Senau argument, which shows the equivalence between entanglement entropy and RT surface. So the proof of this relation in holographic CFT is actually quite straightforward based on the existence literature. Okay, but let me add one more comment on the pseudoentropy in the holographic setup. So actually, in the holographic CFT, we can understand the value of pseudoentropy as the weak value of the area, so-called area operator. First of all, entanglement entropy for the holographic state is known to be equivalent to the certain expectation value of the linear operator, which is often called the area operator. And of course, entanglement entropy is not the expectation value of the certain linear operator at all. It's nonlinear with respect to the density matrix physical state. Nevertheless, entanglement entropy for the holographic state can behave as if we just evaluate the expectation value of the linear operator. It might be obvious from the Yukawa formula where we just computing the area, which looks like the linear operator. And we can show that we can directly show this statement, at least in the two-dimensional CFT with holographic dual, and we can confirm this linearity can hold, at least in the case of entanglement entropy. And then we can just slightly generalize this statement as our pseudoentropy. We have two different states, of course. And so since we can prepare two different states here, I have two different states with different coefficients of the linear combination. And each state, OHI or OHJ, is supposed to be dual to the certain semi-classical geometry. Technically speaking, it is the so-called heavy states. Then we can just directly compute such a transition matrix associated with these two states in the context of CFT. And eventually we obtain this form. And important thing is this form is totally consistent with this expression. So in this way, actually we can confirm at least this linear combination, the number of linear combinations is order 1 compared with central charges. We can show that holographic pseudoentropy can be effectively regarded as the weak value of the area operator. Okay, so finally, let me mention some possible application to the condensed matter physics. So here, for simplicity, let's consider transverse Ising model. Here I'm writing Hamiltonian of the transverse Ising model again, and let's call 0, 1 and 0, 2 as the ground state of each Hamiltonian of this transverse Ising model. So we have different coupling J1, H1 and J2, H2 for each ground state. Then, okay, let's define transition matrix between these two different vacuum state, ground state. And for convenience, let's define the difference between pseudoentropy and the averaged value of the entanglement entropy, like this. So here, S rho A1 corresponds to the entanglement entropy associated with the first vacuum of our interest. And S rho A2 means the second state of our interest. So we just subtract the average value of the original entanglement entropy from our pseudoentropy. And let's call it as the delta S1, 2. And we actually we have observed very interesting things because depending on this coupling, we know that we have two phases which is called the paramagnetic phase, and the ferromagnetic phase for the original transverse Ising model. So we can prepare two vacuum states belong to the same quantum phase or not. Either is okay. And if two states belong to the different phases, in this case, we observe that this delta S12 is always positive. On the other hand, if two states belong to the same quantum phase, like a paramagnetic phase, we can see that this delta S12 is always negative. So in this way, from the positivity of this delta S12 based on the pseudoentropy, actually we can argue whether given two states, at least in the ground state of the system like transverse Ising model, we can answer the question whether given two states belongs to the same phase or not. And yeah, we can generalize such a statement to the more general spin systems like a XY model. And we can also give some nice holographic interpretation of this observation. But this is basically work in progress. So we hope report these things in future soon, hopefully. Okay, so I have finished basically my talk, but let me summarize. So I have defined the entanglement entropy and its generalization, which is we will call pseudoentropy. And this is actually generalization of the entanglement entropy for the transition matrix. So this is basically two-state generalization of the entanglement entropy. And since this transition matrix is complex in general, nevertheless, we have a nice interpretation based on the number of distillable EPR pairs under the LOCC plus post-selection process. And we have also discussed its simple gravity dual, which is just the minimal surfaces in the Euclidean time-dependent Euclidean ADS space. And as an application, we have discussed pseudoentropy can answer the question whether given two states in the transition matrix belong to the same quantum phase or not. And at least in the transverse Ising model, we have seen pseudoentropy can answer this question. So there are many things to do. First of all, it's not yet clear the interpretation of the imaginary part of the pseudoentropy. We have already only discussed the some nice class which takes real positive value of the pseudoentropy, but it's important to understand the imaginary part also. And such an imaginary part sometimes relevant to some dynamical setup, and this is also work in progress. And today I have only discussed the pure state and its reduced density matrix or its transition matrix, but it's natural to ask whether the case of how we can generalize such a things to the mixed state. Although we have already discussed some holographically inspired object in the our first paper, but it's very nice to ask understand this question more generic interest. And it's also very interesting to find is there any further application of this pseudoentropy. So that's it. So thank you very much and thank you for attention.
Okay, great. Thanks a lot for the insightful talk. So are there questions? Yes, please. Okubo-san?
Yeah, thank you very much for your very interesting talk. Can I ask a question about the order parameter?
Sure, thank you very much.
So I naively understand that the sign of this delta is one to detect the spontaneous symmetry breaking. Is that correct?
Yeah, right. Right now, at least this example is correct.
Yeah. And if so, what happens if we measure this delta S12 for the finite size system? So there is no exact spontaneous symmetry breaking.
Well, that's a very interesting question. In this example, we just studied but first of all, we computed it numerically using some somehow finite size of the lattice. But you know, we took size of the lattice enough to have experienced such a phase transition. So yeah, to be honest, I haven't checked whether what happens if we cannot have such a phase transition. But it's likely that, yeah, but anyway, we can check it soon, but okay. Yeah, yeah, it's very interesting question. Thank you very much. And I think in this case, we don't have any significant change of the structure of the entanglement. So in this case, I think it might be wrong, but I think in this case, we don't have such a positive or negative sign change of the response.
Okay. Thank you very much.
Yes, thank you.
There is another question. Yes, please.
Yes, thank you very much for interesting talk. So could you show the summary slide?
Okay.
So you explained that some essence of the pseudoentropies in the post-selection process in the context of the quantum information. And my question is, so what is a correspondence, for example, for the transverse Ising model, what is a correspondence of the post-selection process? Is there any, so you just, for the transverse Ising model, you just calculated between some matrix element of the just two different eigenstate of the transverse Ising models. So in the context of the post-selection process, what is some interpret? Anyway, what is the correspondence in the what is the correspondence of the post-selection process in the transverse field Ising model case?
Okay, thank you very much for asking this. Yeah, first of all, maybe I have to say this is just some calculation. So here I didn't very much care about the real implementation of post-selection in the Ising model, but it can be, for example, realized as you have maybe already told me. For example, we can just first prepare the initial state by measuring the Hamiltonian for the first state, for example. And then after that, we measure something and we post-select another state by measuring the different Hamiltonian for the second Ising model. And then if we obtain the ground state of this Hamiltonian, then we just keep this experimental data. And by using such a procedure, probably we can do the post-selection. I'm not very much sure whether it realistically, it's really realistic setup, but at least formally we can do this, I suppose.
Yeah. So does it correspond to some dynamical quenches of the Ising system? Is it possible such an interpretation?
I see. That's very interesting question. Actually, we now also study some dynamical process like quench you mentioned. But I think in this case we just project all out to the static ground state, but it's really interesting to think about such a more dynamical setup like quench, and it's actually ongoing work. Yeah, and maybe we can report it in future.
Okay, thank you very much.
Thank you very much for asking this.
Okay, I don't see any other questions. So let's thank Kotaro again for the nice talk.
Thank you very much.